I put an alternative title in at the top because well, the problem can be stated also to find all boundary conditions or all D-branes in the Stony string theory with target space R for Liouville, and n-dimensional sphere. Well, of course, if n is larger than n minus one dimensional sphere, if n is larger than 2, then it's not conformal. But if n is smaller than 2, then there is phase transition in the model because the curvature is proportional to n minus 2, and the strong coupling phase is gapless, continuous spectrum, while since the target space is compact, the weak coupling phase is has a discrete spectrum because you have independent rotators in the matter. So there is a transition in between, and actually there is a whole weak temperature of strong coupling phase of the line model, which is gapless, and there is a critical point which is also gapless, but described by another conformal. And well, the problem was to describe all possible boundary conditions on this with this target space. And this our work, I forgot to say that it's the names of my collaborators, Kazuo Kusumichi from Kyoto, and my student Janino Bourgin. And also I should say that our work was strongly inspired by the work by Hubert Sader, Jesper Jacobsen, and the students by Hubert Jérôme Dubai, who is coming to Yale this fall.
But this idea, this principle of two policemen, that
what you will be doing it.
The strong coupling, mass gap, and the weak coupling, different freedom.
Yeah, exactly. Yes.
Oh.
Yes.
This is the first realization of.
Yes, this is a realization of that. Actually, yes, I had a conversation with Dr. on the phone, and we discussed just this thing once a couple of years ago. And, well, it was one of the motivations to do this work. Saller has the idea to, I mean, he thought in terms of the loop class, which is equivalent to the Owen model, and he introduced some special interactions of the loop with the boundary, which are equivalent to breaking the symmetry, the Owen symmetry at the boundary, to subgroup of Owen, with n1 plus n2, etc. is equal to n. Well, you can actually set boundary condition depends on several couplings. In the weak coupling, in the low temperature phase, you don't need to fix the parameters, because once you introduce some anisotropy boundary, since the block is strongly ordered, the boundary will order also. But in the dilute phase, the situation is more delicate, because there, well, each spin. Let me go to the next one. So if I speak about spins, I have to define them. So we treat the system in this way. We discretize by putting a classical ON spin to each side, then consider the system on planar graphs. In this way, we generate the Liouville field. And then we sum over all planar graphs and study the critical properties. This is most conveniently done using the ON matrix model. So, if you want to introduce boundary condition on this, well, let me, I will come to that. Let me first remind.
Why do you keep on the first term in expansion?
Only yes, this is a good question. So this is allowed only in this interval, Otherwise, it's wrong. The spins are weakly. The fluctuations are not large in this interval. So you can neglect the other terms are described by operators that disappear at large distances. Only this is relevant, but this is not true for n larger than 2.
So we study some asymptotics, so that...
No, this is the continuum limit of this model is exactly the same as the continuum limit with the exponent of this, actually. But this is true only in this interval, when the curvature is negative. So this is a well-known statistical model, maybe the most studied statistical model in the last thanks. In the last 30 almost years, 29, because yes, I remember. This formulation of the ON model was introduced in '81 by Ninois. He was a student in Israel, and also Schwimmer, Adam Schwimmer, Domani, and Bucanero. And after that, Ninois established the whole industry of this model. He used the Coulomb gas. He invented the Coulomb gas on the lattice. If you use this description of the model, actually there is a very, very natural parameterization of this interval, which will be important in the continuum limit. If you integrate over the spins, you use the property that integrates S A, S D. A is the favor going from 1 to n. No, then S is equal to delta AB, the only ON invariant tensor. And integral of S is equal to integral S, which is equal to 0. And since if you consider a lattice which has only 3 valence vertices, then you are done with that. You don't need to do more integrations. So whenever you have this delta function, on your lattice, you put a link, a black link. So this is the delta functions, delta symbols, and they close. They form a pattern mutually and self-avoiding loops, and each loop is weighted by factor n, which is the number of flavors. So this is the famous Lugas representation of the ON model. So you have n to the power of the number of loops. The conditional function is equal to sum over all 6 loops, n to the power of number of loops, and temperature to the minus length, minus total length of the loops, where the length is counted as the number of black links. So if you go to the continuum limit, the you reformulate the model in terms of loops, you can forget that n was originally integer number. You can take any real number between -2 and 2, and it will be parameterized by this parameter, p here, which can go from 1 to infinity, but it covers all real values. So, as I mentioned, there is a phase transition here. Here is the phase where the loops are small, they don't grow, and you can forget about them at large distances. There is a critical point, which is described by this conformal field theory, and there is a dense phase, which is described by another conformal field theory with lower central charge. So, and they are called respectively dilute and dense phase of the loop gas.
And those values in the Isaac model?
And n equal to 1 is the XY model of the compactified Gaussian field on the Kostov towers.
It's O2.
O2, yes. You don't have vortices, yes, unless you put them. So now you can, well, the usually boundary conditions are that you don't put anything on the boundary of the lattice. You consider a disk. So you have all loops on the disk, and the loops avoid the boundary. That's all. Now you can put a special interaction on the boundary so that you can change the critical properties of the model on the boundary. So you can do the following, as Taylor and collaborators suggested. You break on the boundary ON to two subgroups, and this is equivalent in the loop gas picture by coloring the loops by two colors, red and blue, and once a blue loop, well, if a loop is in the bulk, then the blue and the red colors sum up to a black, because n1 plus n2 is equal to n. But if the loop hits the boundary, then if you introduce such a boundary interaction with lambda 1 times this Liouville's neighborhood interaction for the first n1 components and lambda 2 for the rest components, I mean, if the loop is blue color, then it will take factor not n but n1, and if it is the red color, it will take a factor n2, which is n minus n1, because you will have the sum of flavors will sum up to n2. So,
but now they can intersect. Yeah?
They cannot intersect.
Why?
Why they should?
Because these are two different groups. The argument was that the average is 0.
No. Only on the boundary, you break the interaction on the boundary by these two terms. But this means that you
inside they are still the same.
Okay. Inside, nothing changed. So if you
Yes, clear.
yes, you have these terms, the product of two speeds on the boundary, and if a loop, a blue loop, touches the boundary, then it will pick. You have to use to integrate over these spins. So you have, so you convenient way to parameterize these two couplings is to say that lambda 1 is lambda plus delta, and lambda 2 is equal to lambda minus delta. And delta is anisotropic coupling.
And inside, in the bulk, you have just S, yeah, which is...
Yes, because the bulk interaction is blind to blue and red. It is just as before. You introduce the anisotropy only in the boundary. These two couplings are tuned independently of the bulk coupling. They are not correlated, and which is quite obvious that if you say, for example, if you take delta equal to 0 and lambda is equal to the inverse temperature, inverse bulk temperature, this would be not sufficient to order the boundary spins. Why? Because each bulk spin has here it has 3 neighbors, but each boundary spin has only one neighbor. So it's the mean field which acts on it is weaker. So you have to insist. You have to put a stronger value of your coupling in order to make the boundary spin order. So there is a whole diagram, phase diagram, depending on these two couplings, which was established and conjectured. Well, Salor and collaborators applied several methods: Bethe-Ansatz, conformal field theory, numerical calculations to establish this pattern of the critical regimes. You have this two-dimensional phase diagram, lambda 1 and lambda 2, and also you can say this is the isotropic coupling lambda, and this is anisotropic coupling lambda. So when lambda, the two boundary couplings are small, you have nothing. You are in the ordinary phase, the ordinary boundary condition, which means that the loops are repulsed from the boundary. Then you make you increase the couplings, and at some along some critical line, actually two branches of this critical line that are not logically connected, the boundary becomes ordered differently, and you have two surface transitions which correspond to conformal boundary conditions. And if you insist more, if you make the coupling even stronger, then you obtain so-called extraordinary boundary conditions, which are also two types. They are divided by this line where the coupling becomes isotropic. So these two phases are not interesting because what happens, not very interesting. What happens is that, say, this is the boundary, and if the interaction of the red loops with the boundary is enhanced strongly, then one red loop glues to the boundary and screens the other loops from the boundary, because the loops are mutually avoided. So it acts as a new boundary, which is of ordinary type. So nothing special happens. So these phases are the same practically as this one. But the critical lines are interesting. So you have Salor collaborators also identified the flows that go from this special point to the two critical phases, but well, they are probably not so interesting.
What are these flows?
Sorry?
What would be the operator which generates these flows?
What are the operators?
Yeah, could you just...
this is the boundary thermal operator 1, 3, and this is you can.
Is it relevant? Is it relevant? 333?
This is.
What are the dimensions of it?
P plus 1 minus 3P.
This looks like 8, yeah?
2 over P.
8
2 over P, yeah.
divided by 4P equals 5. Okay.
But
So-
this is not integrable for.
Sorry?
It's not integrable for.
No, it was numerical.
Yeah.
Anyway, it won't be interesting. I mean, this special point is actually not very interesting. What is interesting for us are these lines, because here you can obtain a boundary conformal field theory with any spectrum, with continuum spectrum of the boundary operators.
A is 2. What is this point?
It's
What
called
boundary condition?
anisotropic. This line
Yes.
is called.
No, the fixed point. A is 2.
Oh yes. This is the well, along this line there is a flow, so this is stable stable point, attractive point along this line,
Yeah.
and this is the anisotropic special transition. This the terminology.
What kind of boundary condition? Conformal boundary condition.
The conformal boundary condition is of the type. Well, I have to parameterize N1 and N2 to tell you. I will do that in a moment. Actually, I will. This is the next transparency. Before that, I would like to just to present the spectrum of the thermal operators on the boundary. The operators N1, which are the L-leg operators. They create L open lines that go from, they start from a point on the boundary. So the boundary correlators, which can be studied in this model on the special lines of transitions, are the following. You have ordinary transition on the left, special transition type 1 or 2 on the right, and L lines here. So the spectrum of these operators, I will show it now, was conjectured. Well, it was very wise and almost, well, it's kind of proved, but not well by studying all the possible asymptotics. So you have n is equal to cosine 2 cosine pi divided by t. So you parameterize n1 and n2 in this way. So it seems not natural, but later it will, this parameterization will become very natural if you consider the functional equations for the correlators. So if you introduce these numbers, so I forgot to. Yes, I didn't prove it. So the range of this parameter R, it is also continuous, and it goes from 1 to p minus 1. So the L-leg operators have the following spectrum. So this is the diagonal R, and you can jump at the integer number from the diagonal of the cast table. So you have.
You said R is continuous, it's not integer?
R is continuous.
It's not a cat stable, right?
Well, it is kind of generalized cat stable, which I'm
Continuous cat stable.
how you continuous? Yeah. So of course, there are symmetries in this representation. You can define delta S is equal to P R P plus 1 R minus P S square minus 1 divided by P plus 1. And all numbers here are continuous. P, R.
Or even P is
No. Sorry. R is continuous. S is also continuous, but in this problem, R is equal to S plus integer. So this continuous cat stable is the whole thing. So the operators that appear, the boundary operators that appear here are the diagonal, then this one, and you go from 0 to P minus 1, but actually you can use the symmetries of the cat table to continue this line to infinity, and this you can safely say that this is the diagonal in some sense.
Can S be more than P plus 1? R? No, in this parameterization, actually, yes, it cannot be. But if you use the symmetries of the cat table, you can continue by identifying this branch to put it here. Well, it's not important.
You're talking about the boundary operators, right?
Boundary operators.
But my question about just the boundary, what would be the conformal boundary conditions? Corresponding. I just don't understand. Is it the
you mean
so,
if you
this is not a Cardi states, right?
it is a Cardi state.
It's a Cardi state.
Yes.
But which
this boundary condition is state R.
But R is continuous as well.
You mean Cardi states?
Yeah, I don't understand the Cardi. So
So
just the formula, you just replay the numbers. I don't understand. Is it satisfy the good stuff?
no, no. Here,
It's a
Cardi considered unitary theory. This is a non-unitary, non-rational.
Yeah, I understand it, but it should be some consistency. Well, I don't know. I understand.
Why do you make here the?
Can you check T equals T bar?
Yeah, T probably equal T bar, but
Then you can undo what more do you want?
you know the modular construct. You know,
In a non-unitary theory, how
I don't understand how the
T equals T bar.
I don't know.
What would be the
I don't know what it is in the theory.
So, but this is non-unitary.
Non-unitary theory.
But conformal bound.
You don't know what are the fields. You can add more fields if you want.
How do you show that all
For
this?
a moment, R is continuous.
So the integral, the pattern will define is only through the analytical continuation, right?
Yes.
There's no
Yes.
way to.
Yes.
These are not even integrable representations.
You can say this is the loop gas. You can define you can say that the functional integral for the loop gas is known.
But it's not unitary.
Sergey, it's April 1st talk, so go easy on the speaker.
Well, I think that Ivan would say it's more than April. It's April 2nd. April.
Yes,
You can say anything you want now. well, Sergei, this boundary condition, the only way to put a label to it is the following. You consider an operator, a boundary changing operator, from the ordinary condition, which is 1, 1, to this. So the dimension of this boundary operator is such that it is R. So you can say, well, if this boundary condition is created by the operator RR, we can label it by RR. But nothing more than that I cannot say. I don't know how to use the model.
So you don't describe the boundary condition, but you describe the operator which changes the boundary condition.
Exactly. Yes. Exactly. So this is the preliminary part. So now I will say what we have done. So we put the problem on planar graphs and encoded it in a matrix model. So this is the usual matrix model, which is already 21 years old. The principle that you just introduce one matrix, which will build the tissue of the wall sheet, and then you introduce this. This is the N matrix. All are Hermitian N by N matrices. Then you introduce N more matrices. Why? This is why I put a vector, which are coupled to this N matrix. And if you build the Feynman diagrams for this model, you will have empty vertex and vertex which is of this type, which describe segment of loop. This is this one. So if you build up the Feynman graph for this model, you will obtain exactly the loop gas.
And what the relation between capital N and small n, lowercase?
Capital N goes to infinity. We will take it infinite.
Just integration over dn small over y.
Okay. My mathematics is very rudimentary, and using let me define dn is equal to product dnii, and then product I with g dnij dn bar ij. So this is the flat measure over the n by n matrices. And same with y, but I put dn because you have n flavors of y matrix. So this is a matrix model, a matrix integral with ON symmetry. And I prefer to write it in this way, by really linear change of variables from n to x. So to kill this term, and you have just this plus potential. The usual variable in this matrix model is the distribution loop for the X matrix. So this describes a disk with mark points and which is covered by non-intersecting loops that avoid. So this quantity can be evaluated easily. It can be done as by integrating over the Y matrices, and since the integral is Gaussian, you obtain a Coulomb gas. So the partition function is just integral over exponent of minus v of xi, and you have a van der Waals xi minus xj squared. And another thing which comes from the integration over the Y matrices, Si plus xj to the power of n. So this is the Coulomb gas for UN invariant quantities. So I should remark here that because of this term, the eigenvalue should be distributed only on the negative real axis. So the potential should be such that it pushes the eigenvalues on the left, otherwise the integral will become ill-defined. So this doesn't pose any problem when n is large, because the integral over when x is positive disappears perturbatively in 1 over n. So now let's define these anisotropic boundary conditions. So we do it by picking another resolvent, which is y. So x is this is the boundary cosmological constant of the corresponding Liouville variety. So y is the boundary cosmological constant, but for this type of boundary. And you put x here, which creates empty points, and y1 square and y2 square, which creates the sources for blue and red loops on the boundary. And well, our aim is to calculate the correlation functions of this and this operator. So they are defined the following way. You just multiply W and H and take the trace. So this is the discretization function with two different boundaries, ordinary and special. And if you put L-leg operators where the two boundaries meet, you have to insert the following matrices. You have to insert actually n different Y matrices, because each Y matrix creates an open line. So this is not to translate in terms of matrices. More difficult is to solve the equations, but it is possible to some extent. So let me go to the next. I described very briefly how to solve this model. Well, you apply the word identities, and it's kind of miracle that these word identities are equivalent to the conformal bootstrap for the 2 points boundary correlation function in Liouville. Well, in the matrix, for large n, the matrix measure is conformally invariant. We know that there is a conformally invariant scheme here, but still it's kind of numerical. So what you do, you just introduce a derivative in the measure, and I mean this is the expectation value with respect to the partition function. O is any matrix, any operator which is composed by x and y matrices. So you take the derivative of O, and here you have the derivative of the action, and that's all. So this is the first word identity. The second word identity is when you integrate over the y matrices, ya. So here you have the same term here, and the next term is the derivative of that comes from the term x, y, a squared in the action. So when you take the derivative, you obtain x, y, a plus a, y, y, a, x. But written in this form, this word identity is not very useful. What you can do is to call this operator, the operator O, and then express this one with this. So this identity is equivalent to this one. So this is you just inverse you inverse the adjoint action of the commutator of the multiplication of x, and this is done this way with the contour integral. The contour integral is around the negative axis where the eigenvalue. And you can prove it. Well, you can go to take Laplace transform and then an inverse Laplace transform. So this is actually the inverse transform. Geometrically, this equation means that whenever you have a wave matrix, you can replace it by two wires, and at the end of the wires there is a derivative. So you can systematically diminish kill the wave matrices whenever they appear. So when you do that, you obtain loop equation for the usual correlator, or with ordinary boundary conditions, which is this part is the same as the equation for the wave matrix model. And the solution of it is just square root of something. But this term is the new term, so it appears because when you differentiate with respect to x, you obtain y, insertion of y. So you have to kill this y. You apply the second identity, it creates wires that with the derivative which kills the second y here. So you obtain 2w, and they are related by convolution. So this convolution comes from the definition of the second identity. So by using the property, this nice property of the convolution, and summing this equation and the equation x replaced by minus x, you obtain a functional equation for the loop correlator, which can be actually this is written only for the singular part. So we take the continuum. No? We neglect all polynomials or all regular functions and consider only the scaling part, and it satisfies this equation where in the scaling limit we can neglect there is also x to the fourth. So when these two coefficients become small, if this is small, this should be small also, and we obtain, so this vanishes when the bulk cosmological constant is 0, so it's the critical value of this beta reaction. And the second term disappears when the temperature becomes critical.
How do you know the critical exponent?
The critical exponent, you find it from the equation. If you take that, say that this is 0, then taking the equation you have x. So w is x to the alpha. So you have x to the 2 alpha plus minus x to alpha plus x to the alpha minus x to the alpha, and multiplied by twice cosine I divided by t is equal to some to 0. Yes, to 0. Okay. So you have to cancel all these terms, and from here you obtain alpha is equal to 1 plus 1 over t. Actually, you get plus minus plus 2n because you have here you have the periodicity. But you take the lowest possible exponent because only it should survive, survive, and this is 1 minus 1 over P. So this is the weak, low temperature phase, which is critical, independently of the temperature. Then you tune the temperature, and logically, the critical temperature is when the second term, the subliminal term, becomes critical. Sorry, not critical. Becomes of the same order as the first one, and from here you obtain the dimension of the temperature, and the temperature is proportional to x to 2 divided by p, the dimension of x. In this way, we obtain the solution. And the solution is, I mean, if you, I forgot to say that, in general, the eigenvalues are on some cuts on the negative axis, but in the continuum limit, the left side of the cut goes to infinity, so we can say that the cut is infinite, which can be resolved by this substitution, which is standard in Liouville theory. So the boundary cosmological constant is equal to the bulk cosmological constant to power 1/2 or some other power times cos tau. I wrote the complete solution here, which is also easy to be obtained, where U is the susceptibility of that is the 2-point function of the identity operator on the sphere, and W is given by the sum of these two terms. So this is the disk 1-point disk correlator of the perturbative theory with temperature, bulk temperature T. And the susceptibility is obtained by this equation, which is this transcendental equation, which is obtained as follows. We can find W from the dilute equations, and we can find also the bulk 1-point function on the disk similarly, W is the derivative with respect to x of the disk partition function, and the other quantity is the mu of the same disk partition function. So if you take the mu derivative of this and equate it with the x derivative of this, the condition that the two derivatives are the same is this one. So this is the simplest way to obtain that. Otherwise, there is a hard way to obtain this equation, and it is by analyzing the exact solution of the OM model on the random net is given by Einard and Christiansen. But it is, even if you know the solution, it is not easy to extract this equation from there. So this partition function corresponds to Liouville theory, which is perturbed by a thermal operator 1,3, I have how much?
No, it's okay. So you can order you want.
If I changed a little bit the normalizations, the transcendental equation, but you can solve it in terms of, you can expand it in terms of T. And you can integrate twice to obtain the partition function on the sphere, and it is given by this expression, which actually Alyosha Zabolotchikov taught me how to solve this equation, how to obtain this series. And well, Alyosha, together with Sasha Belavin, checked that up to 4 terms, this expansion is reproduced by Liouville gravity. So now let us consider the equations for the correlators. Using the same trick as before, you obtain, this is too small, I will draw it on the so you have the correlator DL, and so you have n Y matrices here. You apply to the first Y matrix the second word identity, and you obtain that you obtain a wire which ends here, where another Y matrix with the same flavor. So in this way, the world sheet is cut into 2 parts, and here you have W, and here you have the correlator with one line less. So this is as simple as that. And this equation is actually projection of the functional equation for the discorrelator obtained by by the two homologicals and Valery Fater in 2000. Yes, the XZ, the XZ paper. Actually, they wrote in the conclusions this equation. They calculated differently the 2-point function, but the equation is essentially that. Well, of course, this is in the case when is equal to 0, so W is given by only one cosine function. Otherwise, we have more complicated here. If you do that, we will go. We can kill all the lines until here. So, what to do if you have if you have no more lines? So in this case, you apply again this word identity, and you obtain the following. Well, you take the case when you have one Y matrix here. So you apply the word identity, which will end here somewhere because this boundary contains Y's. So it will cut the world sheet into 2 parts, and here you go. Here this is D1, this one, and this is D0. So you have no one. So you have quadratic identity for the D1 and D0 correlator, which I will skip that. Which for the continuum limit has the following form. D1, bar means x replaced by minus x. So D0, D1 bar is equal to combination of W of x, W of minus x with this coefficient, and also mu boundary and x times the boundary temperature. So when there is no boundary temperature, this is again the XZ equation because of this identity, which also can be proved, but I don't have the time. It's almost obvious. Actually, it is obvious because the D2 here is boundary correlation function where when the left boundary is allowed to touch the right boundary. So if you write it as a geometrical progression, you will obtain that D0 with the operator of type 2. Sorry, no of type 2. D0 is essentially D0 1. And D0 2 is 1 over 1 minus D0. And this is the geometric progression, which is 1 over D0 2. This is against the XDZ equation because actually this function can be put on the right as here using the fact that that it is the inverse of D01. Actually, D01s are the correlators that correspond to the same boundary condition and which satisfy this D01 is designed in such a way that it satisfies this transition also, this equation also for L equal to 0. So these two functions are actually related by boundary reflection. So in this equation, instead of oops, I really have no time. So but I will finish. If you write these equations, you can easily extract the singularities. It's as simple as that. So you obtain this critical behavior, and from here, by the KPZ correspondence between gravity and Liouville, you obtain the spectral, conformal dimensions of the boundary operator, which are the same as conjectured by Salor and collaborators. So when the two temperature constants are 0, we obtain exactly the same functional equation as the letting Liouville, boundary Liouville gravity. But when they are not 0, our equations should describe such a theory. So you have two boundary conditions, two different boundary conditions, and you have perturbation, thermal perturbation in the bulk, and also thermal perturbation in the boundary with another constant. So that's it. We are still not very satisfied by the fact that we cannot actually evaluate this result. We can see how the two-point function changes with the boundary parameter related to the ordinary boundary, but we cannot apply the same equation for this special boundary. Well, this I don't know. Well, maybe there is some meaning in that. It's quite obvious from the word identity that it's when you apply it, it creates ordinary boundary and not the other side. So here there is still some unknown information about the scaling of the special boundary in continuum delete. I think that this is the time to my battery is down. Thank you.
Any questions?